minute, I'll share my screen with you.
Mhm.
So let me know if you can see the screen.
I can see it.
Okay. How about you, Anirudh?
Yeah, I can see it too.
Okay, so we're going to start looking at Verilog, some brief history about how Verilog came into existence, and then we will start looking at Verilog, actual Verilog as a language, as a hardware description language. As I have told Anirudh, I will tell the same thing to you, Ruth, that if you don't understand anything, if you feel the speed is too much or too less, or any problem, you let me know. We will try to fix it.
Okay.
If you have any questions during the class, you can ask them at that time, or if you can come across any questions later on, you can note it down in your notebook, and we can take it up in the next class.
Okay, sounds good. Thanks.
So this is Verilog to start with. So let me see if I can. Yeah, I can do that. Okay. So what is HDL? Verilog is called a HDL. So HDL stands for Hardware Description Language. What it is a text-based method for describing hardware to a synthesis tool. So synthesis tool is basically a software, synthesis software, where the design entry of the hardware design is in this language called Verilog. And Verilog and VHDL are called HDLs, hardware description languages. So what we do is we describe the hardware, not program the hardware in a sense. We describe the hardware to the synthesis software or the synthesis tool, which will then convert that Verilog language to gate level netlist. So there are certain advantages that we have when we use HDL methodology, hardware description language methodology, over the old schematic entry. So before Verilog and VHDL came into picture, people were still designing chips, right? Verilog and VHDL is basically used to design a chip, a hardware chip. Before these languages, people still were designing chips, but those were done in schematics using gates. So there are certain advantages that we have when we use Verilog or VHDL or schematic design entry format. What are those advantages? If we use this concept of Verilog, it will produce correct designs in lesser amount of time. It will produce larger and more complex systems per unit time. So you can design more complex and much larger systems in a given amount of time compared to schematics. It will shift the focus to specifying functionality of the design. When we did schematic design, a lot of time and energy was spent in worrying about the connections, the gate connections. What is input connect a particular gate? What is the input connected to? What is the output of that gate connected to? Is it correct? Is there some connection missing? So a lot of energy and a lot of time was spent on the connection aspect of it. Whereas with HDLs in Verilog or VHDL, we spend the time from specifying the functionality of the design, and we let the synthesis tool worry about the connections. So our energy and time as a designer is spent on the functionality, which is where which is the right thing to do. Synthesis tool will automate the details of connecting gates and devices. So the synthesis tool, so the software, will take Verilog design as the input and convert the Verilog design to gates and the overall netlist, where it will consist of gates and interconnections between gates and other components. So the left hand side that you see here was the old schematic level flow, or the schematic based design flow, where we had a schematic which was man-made or human design schematic. We created a netlist of this. Then we could do a gate level simulation of that netlist. And then after the gate level simulation was done, where we were sure that the design was working as per the design specifications, then we implemented that design and manufactured a chip out of it. Compare that to a HDL based design flow on the right hand side. This text mentioned is here is a Verilog design, the HDL in Verilog format. Then we perform a HDL level simulation where we write a test bench in Verilog. So we design and the test bench, we simulate the design, and we look at we generate a timing diagram or simulation results where we analyze the results. If those results are correct, we go forward. If those results have some errors, we go back and fix the errors here itself. So this is an iterative process which goes on till we solve all the functional problems as per the design specifications. Once the functionality is correct in simulation, then we take the design, not the test bench, only the design to synthesis and backend flow. So this is called a backend flow. Synthesis, placement, and routing. So synthesis, netlist generation. In the implement phase, you have mapping, placement, and routing, and finally, in case of FPGA programming. In case of ASIC, we do send it for ASIC manufacturing. So this is the HDL based design flow, where the design part of it is done in Verilog. All these other things, simulation, so design and test bench is done manually, but the simulation, synthesis, netlist generation, backend implementation, all of done is done using software tools automatically. I mean, you have to run. It's a click button flow, which will go from one stage to another stage. It's pretty straight, automated, and straightforward. So the manual intervention required in this section is very minimal. The design part of it is where you spend a lot of time. So do you understand the difference between two design flows? Or any questions?
No.
No.
So if you would like to note down this flow or note down any points, you're free to do so. Later on, I would be sharing the recording of this presentation. So if you want to take some time and note down this flow or any other points, you're free to do so. Okay.
Yeah, that's
Yep.
fine.
Okay, going forward. So the other advantages of HDL based design methodology is we operate at a higher level of abstraction. When we do schematic designs, we work on gates at a gate level abstraction. So gates and components from the library. So we take the gates and the various components and then we interconnect them and create a schematic or a netlist out of it. When we work on HDL based design methodology, we work at Verilog HDL language based abstraction level. So we are not worried about gates and components at that time. We use the language and the language syntax to describe the design. So we are operating at one level of abstraction above the gate level, where we operate in schematics. Another advantage is we can debug earlier. So this is a very key advantage. When you do design in Verilog, you can write a test bench and you can debug the design. Make sure there are no errors whatsoever at the simulation stage itself. If there are any errors, you can fix the errors at the simulation stage and then go on for the backend process. There is a certain thing called parameterized design when we use Verilog, uh, where we can quickly make whole scale or large scale changes, modifications to a design. So, parameter is a concept in Verilog where, for example, burst width. We define a parameter called burst width. We define it once and then we use that instead of hard coding. Let's say the I want to develop a processor which is 8-bit at this moment. So I will declare a parameter called burst width. I will declare burst width equal to 8. Use that label burst width throughout my design. So I'm not hard coding my design where it is 8 bits everywhere. Let's say that parameter, the burst width itself is used at 100 different places in my design. So at 100 different places, I'm not using the actual value 8. I'm using the label called burst width, which is actually the parameter. So I declare it once and I use it multiple times. In case tomorrow I want to change my design from 8-bit processor to 16-bit processor, all I have to do is change it at one place. So wherever it is declared, the parameter called burst width will change from parameter burst width equal to 8 to 6 to parameter burst width equal to 16. Throughout my design, I'll be using the label burst width. So instead of 8 bits, it will be 16 bits. I can make I can make a lot of changes in a single go basically using this concept. This is not possible in schematics. This is possible in a language based methodology like a Verilog based methodology. Can quickly specify desired behavior. So my focus is on the desired behavior. So let's say I want to design a simple up counter with a reset. So how do I do it? This is a simple piece of Verilog code. If reset equal to 1, count gets 0. Else count gets count plus 1. So if reset is activated, I'll reset my counter to 0. Else, means if reset is not activated, I will count upwards by 1. This is a very simple code, but this is how we can focus using the language on the desired behavior of the design, which is up counter with reset. I don't have to worry about counter, how many bits the counter is, how the reset is connected to the various flip flops. Is the counter connecting from one stage to the another stage at the in the right way? So all that is schematic related details, which I leave it up to the synthesis tool to take care of. I do this in Verilog and feed this to synthesis tool. The synthesis tool will implement a counter and make the necessary internal connections. The focus is on the behavior. We can target multiple devices, which is called product migration. So the same Verilog code that I designed today, let's say I am developing a FPGA out of it. So I can use this FPGA as a and develop a prototype of my product. Once the prototype works correctly as per the requirements, later on, if I'm going to sell my product in very high volumes, a few million devices, then it is financially more sound to convert that FPGA to a ASIC device. Because the ASIC once manufactured will cost less than a FPGA, as we have seen during the earlier last class. So ASIC cost will per chip cost will be less compared to a FPGA. So if I plan to sell millions of devices of my product, it is better to do ASIC later on. In that case, I can take the same Verilog code and make a ASIC out of it. Obviously, there are certain what do you say changes when you implement that using ASIC technology, but I don't have to do that at a Verilog level. The changes are in the backend phase of synthesis and after synthesis. Verilog code at the front end side remains the same, whether I'm trying to implement a FPGA or ASIC out of it. So I can target multiple devices, which will help me migrate to a different kind of product. Even FPGAs, maybe today you are developing using a Xilinx FPGA, some other FPGA. Tomorrow you are trying to develop the same design using an Intel FPGA or a lattice semiconductor FPGA. The same concept applies. Same Verilog code can be taken and implemented on a different target device later on. I don't have to change my Verilog, assuming the Verilog that I have developed is technology independent. So normally what we do is the Verilog that we develop, we don't include any target specific components. For example, if I'm using a Xilinx FPGA today, I will try to develop my Verilog in such a way that I'm not using any Xilinx specific components of Xilinx libraries directly in my Verilog code. My Verilog code should be as generic as possible. No technology dependent components of this FPGA should be included in my Verilog code. If I do that, I can call my Verilog code as technology independent. If I have a technology independent Verilog code, I can target it to other devices later on. If I have certain technology dependent components, then I have to make those changes where similar components from the other technology are used in that case later on. Okay.
Okay.
Any
Yeah.
questions?
No.
No.
HDL is more universal than schematic tools. Obviously, HDL is a language, right? So the language is much more universal. It's a free language. Nobody owns the language. It's a IEEE format. It's a IEEE standard, basically. So the language can be used by anybody. It promotes design reuse in an IP format. So if you remember, we talked about IP cores when we saw initial design methodology. Nowadays, in today's technology, I mean the way products are designed today, we need new products to be launched every maybe 6 months or so. So let's take a smartphone for example. Every large top-end company, the leading company, they have to launch new products, except Apple maybe, have to launch new smartphones every 6 months or so in the market. So if you want to launch a new product every 6 months or so, you have to design a new chip every 6 months or so. Designing a new chip from scratch in 6 months is next to impossible. Okay, so what people end up or what teams or companies end up doing is they try to use certain things called IP cores, intellectual property cores, which are basically small designs. They try to get these small designs from some other companies. They license them, license those IP cores from some other companies, or they just buy them outright, the source code for it. Then they use that IP core in their own designs. So it is basically integrated. That IP core is integrated in their existing design, and that's how you build bigger designs. And you build bigger designs quickly. If you can build bigger designs, which is a requirement, and the requirement is to build them quickly because I want to launch my product later on in the market. This is how you can do it. So this IP core again will be developed using Verilog language by the third party company. And that Verilog based IP core will be licensed or sold. The source code will be sold to other companies. So it will promote design reuse. I can take some other IP core from somebody else and integrate in my own design. All this is possible because we are using a HDL based design methodology. This is not possible in schematics all the time because schematics, the gates and components are technology specific components which may not work with the other technology. Verilog source code works in the other design as well. So it's a very key advantage of Verilog over schematics. Something that we have to remember is HDL is not a programming language, it's a description language. A lot of people come from software background, right? They come and try to learn Verilog to understand how hardware design works. So, coming from a software background, people are used to a programming environment, right? You take a language, you take a IDE from somewhere, you develop a program, you run a program, you compile and run the program. So the program, you basically program a software model and you execute the software model. So the concept is you develop a program and it gets executed on a processor or motherboard somewhere. Hardware language works differently than a software programming language that we will see later on. There are key differences. So the concept you have to understand is you are no longer in a software programming domain. You are trying to develop a hardware design in a hardware domain, which will actually work as a real life hardware somewhere down the road. So there are key differences that we'll see later on. That has to be kept in mind. Another thing is we talked about level of abstraction. So Verilog or VHDL is one level of abstraction above gates and above other components of schematic design. But still it is not that abstract that we can, it is abstract, but we cannot implement. I cannot, like, for example, apply this equation as the input, which is basically a digital signal processing algorithm for filters. And I can feed it. I cannot yet feed it to a Verilog, or I cannot just type this line in Verilog and say implement this design for me. So Verilog is abstract, more abstract compared to gate level schematics and component level schematics, but it is not that abstract yet, where I can just feed any equation to it and say implement this system for me. To implement this kind of system, I have to break it down. I have to study first of all what needs to be done, break it down into stages, and then implement Verilog source code for those stages. Have any of you used any system level languages in your graduate programs, for example, MATLAB or Python or something like that?
Little bit, not in like very advanced level.
Yeah, but have you had an introduction to it and maybe ran a couple of programs at least in what MATLAB or Python?
Yeah, MATLAB. It was an undergrad, so it was very
Okay. How
long
are you
before.
good?
Same thing for me. I did not work a lot on MATLAB, just a little bit in undergrad.
Right. So if you remember some things along some things that you did in MATLAB, so this equation can be built in MATLAB pretty easily. It's a system level language. Okay. So I can design the
Mhm.
system in MATLAB and then I can try to convert that system to a Verilog or build it from scratch. So MATLAB has a way of converting it to Verilog internally. So MATLAB is a software in programming language. So I can implement this kind of equations in a software environment relatively easily. But to implement these equations on a hardware platform using Verilog, lot more effort goes into place. I mean, I cannot just implement the equation as it is. So Verilog is improving slowly over the years. Verilog has improved quite a bit, so, but we have not reached a stage where Verilog can be used as a ESL, system level language, basically. So that high level language option is getting developed at the moment. Maybe another few years down the road, it will reach this stage. At this moment, I cannot do this in Verilog. So you have to understand the reason behind talking all this is, I mean, you have to understand the limitations of the language. So it's a design description language. It's abstract compared to schematics, but it is not that abstract that I can implement any equations, any complex equation just as it is. I can implement this equation, but in a different format. So that's a current limitation. Verilog and even VHDL began their life as hardware languages, as simulation tools and modeling tools back in early 1990s. Okay, and then hardware synthesis was developed during the second half of 1990s. Synthesis again is a concept which will convert the Verilog and VHDL code into gate level netlist, which can then be used for design purpose. So what we have to do is we have to use a subset of Verilog and specific coding styles to allow synthesis to infer correct and realizable hardware. What that means is Verilog design is the input to the synthesis tool. Not entire part of Verilog can be synthesized into hardware. Only certain sections, only certain percentage of Verilog can be synthesized into hardware. That percentage is around 40-45%. Rest of the language can be only used for simulation or modeling, software modeling, or hardware modeling in this case. The subset of Verilog which can be synthesized is part of the Verilog language. That part or that subset can be synthesized and converted to a FPGA or a ASIC or some other FPGA, one of the FPGAs or ASIC. Synthesis tools will take Verilog as an input and it will infer, means it will try to understand what the Verilog code means, and for that Verilog code, what is the hardware netlist that has to be generated. That process is called inferring. So it will infer the correct hardware out of the Verilog description that's given to it. That is the role of the synthesis tool. So you have to also understand to a certain extent how the synthesis tool works. And there are certain styles, coding styles, that if you follow them correctly, synthesis tool knows what is that Verilog meant to do and what is the hardware it is meant to infer or implement out. So to summarize, I mean Verilog and VHDL began as simulation tools only. Later on, synthesis process was developed where these languages could be converted to netlist and used on FPGAs or ASIC in hardware. But to do that, only a subset or certain part of the language can be used to do that. Where the synthesis tool will take that part which is synthesizable to infer correct hardware out of the Verilog design. So, in graphical format, this is my entire Verilog. This is my synthesizable variant, which is a subset of the entire variant. Only the synthesizable Verilog can be synthesized to design hardware in a FPGA or ASIC. The rest can be used, or the entire other Verilog can be used for simulation purpose. Test benches, I can use the entire Verilog for test bench purpose. Why? Because I will never synthesize a test bench on my chip. Test bench is a testing environment. I will never implement a testing environment on the chip. I just use it to test my design at a simulation level. Then the design itself will go on the chip. The test bench, which is for the testing purpose, will remain at a software environment level or the simulation level. So for test bench writing purpose, I can use the entire Verilog. But for synthesis and implementation on hardware, I can use only synthesizable subset of Verilog. So do you understand this concept? Do you get this concept? Because it's very important to know this.
Yes.
Yeah.
Okay. And we'll see what those subsets are as we go forward. So there are certain learning hurdles when you learn Verilog to design hardware, right? Coming from specifically a software programming background, you will try to write HDL code in such a way that eventually that code will be executed by some processor on the FPGA. So FPGA or ASIC for that matter. When FPGAs or even ASIC nowadays don't have processors on them. FPGAs, latest FPGAs have an inbuilt processor on them. But HDL language is not a software programming language. Software programming language works in a way that it works sequentially. Whether you have, let's take a C program, because you might have done embedded C program. Whether your C program is very small, 10 line, 20 line code, or very long or big program, thousands of lines. Doesn't matter how long or how big your program or how small it is, it will always execute sequentially, first line to last line. And that executes on either if you're working on your laptop, it will execute there, or if you have an embedded microcontroller, there is a processor inside the microcontroller which will execute the C program. The C program will be executed sequentially, one after another line. FPGAs work differently. FPGA is like a clean blank slate given to you. FPGAs have a lot of parallelism built into it. So entire chip can work as, it doesn't matter. It depends on your logic. It can work. It has a lot of parallelism built in, so your logic can work parallelly, basically. So FPGAs work differently compared to microcontrollers, specifically comparing to microcontrollers. Microcontroller, the entry is in C language, where the C language program will be executed sequentially on the microcontroller. On FPGA, the Verilog design, the entry is in Verilog or VHDL design languages, and it will work parallelly based on your design. Because hardware design has to have parallel logic. That is how hardware works. It doesn't work sequentially, it has to work parallelly. FPGAs support that. So yeah, when you write or when you describe designs, so I will always repeat that I don't program my FPGA, I describe my design on the FPGA. When you do that, you have to keep this in mind. Any questions on this slide?
No.
No.
So what is Verilog? Verilog is a hardware description language. See, when we started out with Verilog, 90s, uh, the way it was divided was North America, right? So US, Canada, mostly US, Canada, because South America doesn't really do a lot of this. North America was all Verilog. Europe was all VHDL. That's how it was divided. If you look at it now, it's practically mixed, and most of the industry now, the way it is divided is, most of the companies use Verilog. If you go to universities, a lot of VHDL is still used. That's how it is divided now. But when it started out, mostly US or North American companies were using Verilog. One of the advantages of Verilog is the syntax is very similar to C language. And compared to VHDL, it is simple to learn. So VHDL was a language which was developed by Department of Defense, US, DARPA agency. Right? They developed it and then they released it, this language. It was based on a language called ADA language, which is used for software programming. So all these mission critical systems like air traffic control, the metro stations, the metro systems, etc. All that was developed using ADA software language, by which was also developed by DARPA before DoD. Based on ADA, VHDL was developed for hardware design, and it was released to the entire industry to use it. It is a very tightly typed language. So learning VHDL is comparatively more difficult than learning Verilog. Verilog, the syntax is more similar to C, and it has more flexibility, the way the language is defined. So it's easier to learn Verilog. So that's also might be one of the reasons why Verilog, the usage of Verilog increased over a period of time. Where nowadays in the industry it's all standardized to Verilog most of the time. Very few teams will still use VHDL, but that will be very less percentage. Mostly is Verilog in the industry. Yeah, so we already saw why use a HDL compared to schematic designs. We can design complex and bigger systems. We can describe or focus our our efforts and time on the functionality and input it to the synthesis tool. We can debug and explore the design at a simulation level. But why not use a general purpose language, right? So there are general purpose programming language like C language, for example, because C language was still in place and it was still popular at that time. There are certain differences, or there are certain things the C language won't or cannot do for us, what hardware description language do for us. A support for structure and instantiation of designs. We'll see what this means later on. Bit level behavior. So C language or embedded C language specifically has evolved to a extent where we can do bit level behavior also. We can control it at a bit level behavior. Bit level behavior means, let's say there are 8 bits, uh, 8 bits, what do you call, on the output bus maybe. And those 8 bits are individually connected, let's assume, to 8 different LEDs. Very simple design. I can individually control the operation of 8 different LEDs which are connected to individual bit of the 8-bit bus. So now using the current version of embedded C language, I can control those. But many years ago, I could not do a bit level control in embedded C language, which I can do in hardware description language. And the point number 3 and point number 4 are extremely important because these are still not available in C language or most of the programming languages. But support for timing and support for concurrency. So when I design hardware, because that's what I'm designing when I design a chip, I need to control the timing on my chip. And I need to control the concurrency or concurrent execution on my chip. Timing is basically, so if you buy any smartphone, for example, if you buy any processor or you look at any processor, typically the specifications of the processor will be published. So they will say that, oh, it's a 1.3 gigahertz processor or a 1.7 gigahertz processor. That whatever that clock, that's the clock frequency of the processor. So the clock frequency is the key parameter. So internally, all the processor is working with respect to the clock frequency. Internally, there is a lot of logic, millions of gates on the processor. All of them are using that clock for internal operation. I need timing control inside the chip to control various aspects of my logic. So that timing control that I can get using Verilog, specifically, for example, I cannot get that using a C language or any other programming language. So Verilog gives me that functionality to control timing using the clock frequency on board. If you look at any board, FPGA board or any other board, general PCB, there will always be a crystal oscillator which is generating the clock for that board. Have you seen any board with a crystal on it? Hello,
Yeah.
right? So you'll see a small crystal on the board which will generate the clock frequency for your design. That clock frequency is taken, is connected to your chip, and your chip works with respect to that clock frequency. Internally, either stepping it down or stepping it up depending on your requirements. And all your timing is with respect to that clock inside the chip. So that's the support for timing aspect. Support for concurrency aspect is the parallel execution. Concurrency means parallel execution of logic. So in the hardware, for any hardware, parallel execution is extremely important. Whereas in a typical software programming environment, you don't get that. Nowadays, you are getting parallel computing environments, but that is still in the very early stages. It's very difficult even now to control parallel execution, which is very easily available for me in Verilog language compared to C language or any other programming language. So those 2 points, timing and concurrency, is very important. Verilog versus VHDL, we just talked about it. Mostly it was Verilog in North America, VHDL in Europe. Nowadays it's Verilog mostly all over the industry, VHDL mostly still at university level. Any questions?
No.
Okay.
No.
So what's my modern project methodology, right? Let's look at that. A design methodology for that. So this is for FPGA design, but the same applies for ASIC also. This is my Verilog code. This Verilog code will be described or designed using the design specifications. We talked about design specifications earlier. When you develop a product, your a team of system architects would understand what a product needs to be developed, what are the functionalities required. Then they will partition that product design into software and hardware. Under hardware, they will partition again under chip design and PCB design. What can be done using discrete components on a PCB? What can be done using a chip? Whatever can be done using a chip will come as a design description here or a design specification here. That design specification is the reference for which I will develop my Verilog code. This is my Verilog code. My Verilog code will be synthesized by the synthesis software. Verilog code will be converted to gate netlist. This netlist is of gates which are generic in nature or called primitives, basic gates. Then I use a particular target technology. Let's assume a Xilinx FPGA. So this generic netlist or a netlist consisting of generic gates then will be converted to a netlist with technology specific gates from that library. So CLBs are part of Xilinx libraries, so configurable logic blocks. CLB stands for configurable logic blocks. So the generic gates will be replaced by all technology specific gates from the library. And then this technology specific gate netlist will be placed on the chip and routed. So this is placement and the interconnections will be routing. This will be placed and routed on the chip, and then I program the chip with this netlist. So the chip will start working as a Verilog code that I have described here. This is the modern design methodology or project methodology for all chip designs. This is in a generic way. So whether it's a FPGA, ASIC, in case of ASIC, the placement and routing or the backend steps will be much more. There is something called, there is a lot of backend processor where we do design rule checks and other things. So, but more or less the flow remains the same. You start out with a Verilog or VHDL code, you synthesize it to generic netlist, then it gets converted to technology specific netlist. You do the backend process of placement and routing. Any timing analysis, static timing analysis is done after placement and routing. Finally, the chip is programmed for the functionality, which was described in Verilog format. Any questions on this slide?
No.
No.
Okay. Okay, fine. So there was a brief overview or history of Verilog. So what are the objectives? We are trying to understand the design methodologies using Verilog, design digital circuits using Verilog. That's a key objective here. Verilog can be used to design digital circuits, not analog circuits, only digital circuits. For analog design, Uh, if you look at the industry, it's the design aspects are divided into analog and digital domain. For digital domain design, you use Verilog and VHDL. For analog design, which works at a CMOS transistor level, we have a language called SPICE. Okay, you might have used it in your grad school somewhere. So SPICE is a language mostly which is preferred to do analog design, and that's a different domain. We don't look at that. It's a different problem to solve. When you use Verilog, it's used to design digital circuits. That's where we have our focuses. The target audience, we have to have some basic understanding of digital logic concepts. If you have worked on C or similar languages, that's going to help you. If you use any software tools like compilers and other things, it's going to help you understand this better. So that's why we did an overview of digital logic design. We talked a little bit about C language and the differences between C language and Verilog. We talked about some of the software tools that are used in different methodologies, C language based methodology and Verilog based methodology. So actually Verilog was a proprietary language. It was invented and developed by a private company called Gateway Design Automation back in early or late 80s. They developed their own simulator in 86, which was very popular at that time, Verilog XM, and they sold a lot of them. In late 80s, early 90s, the synthesis software was developed by a company called Synopsys, which is now the number one EDA company in the market. Right? They developed the synthesis tool, which will convert the Verilog code to synthesis netlist, gate level netlist. Late 90s, late 80s, early 90s, actually, this company, Gateway Design, was acquired by Cadence Design Systems, which is number two company in EDA market. It was still proprietary language, but later on in 90s, it was released to the industry as a IEEE standard. So from that point onward, it became an open language. Nobody owns the language. No company owns the language. It's a IEEE standard. So it's a free language. And there is a IEEE standard means uh, every few years there is a committee, worldwide committee where people from all over the world from industry and from academics are involved in that committee. They are part of the group which looks at the Verilog language, and every few years the language gets updated with new features, new things. So that's a part of being a IEEE standard. Every few years the language will be updated. So like any other language, we have something called LRM for Verilog, Language Reference Manual. So that's just, I don't know whether you have looked at LRM ever, but LRM is a very basic format uh, in Backus-Knorr format actually. So that is the base format on which the language is developed. So that language manual is very important. So any Verilog software or any software which says it supports Verilog has to follow that LRM. That's the like the Bible for your Verilog. You can say that. So late mid 90s, Verilog became an open language, and it has been open language forever. What we'll see as a part of the Verilog course is how do you model or how do you design circuits using Verilog. There are two methods, main methods of modeling or designing using Verilog. One is called structural modeling, one is called RTL modeling. So over the course, over the period of the course, we'll see that RTL and HDL, this terminology will be used interchangeably. Before HDL or before Verilog was called HDL, they were called RTL. RTL stands for Register Transfer Language. So when it started out, it was called RTL. Any language which was using that format was called RTL. Later on, they renamed it to HDL, Hardware Description Language. So Verilog and V. Earlier there were a lot of languages. Later on, it got standardized to two languages, Verilog and VHDL. Both of them are called HDLs, Hardware Description Languages. So sometimes you will see HDL or sometimes you will see this RTL terminology used. It's the same thing. So the Verilog design can be, or digital design can be developed using Verilog, using structural modeling concept or RTL modeling concept. RTL modeling is also called behavioral modeling. We'll see all what all this means in the next few slides and few classes. A digital design consists of two kinds of circuits, as we have seen in the digital logic refresher part: combinational circuits and sequential circuits. So, Anirudh, since we have seen this, can you recall what are some examples of combinational circuits and sequential circuits?
Yeah, all the gates and stuff.
Are part of?
Some uh, uh, basic gates like AND and OR are combinational circuits,
Okay, those are the basic gates. Anything else?
and logic gates and universal gates,
Right. So
and
NAND and NOR are universal gates, right? You can build any gate,
yes,
basic gate like AND, OR, XOR, etc. using NAND or NOR gate. So NAND and NOR are universal gates. So those are gates. Any other circuit that you can recall?
uh, mux, demux, decoders, encoders,
Right. Those are again part of combinational or
combinational
sequential
circuits.
combinational circuits.
Yeah.
Okay, so multiplexer, demultiplexer, encoder, decoder, demultiplexer. I already said adder, subtracted, right? All these are part of combinational circuits. These are examples of combinational digital circuits or combinational circuits. Any examples from the sequential circuit section?
ROM, RAM,
Memories, okay. Anything else?
mem state diagrams, FSM, finite state
That's
machines.
to be classified as a separate category here. So we'll keep FSMs separate for now. So what's the most basic part of any sequential circuit, or the basic component of any sequential circuit? We saw
Truth
that
table.
truth table is for your combinational circuits, or even for sequential circuits, fine. But that's operational. Basically, that's how the circuit or component behaves. The results are right.
Mhm.
So if you remember, we saw flip flops, right? Flip flop
Yes.
is the most basic component of any sequential circuit, and using flip flop, you can build bigger sequential circuits like registers, simple registers, multi-bit registers. Then you can have shift registers. Then you can have counters. Counters can be up counters or down counters. Up counter with reset, or up, let's focus on up counters. Up counter with reset. Up counter with parallel load feature, etc., etc. So we saw some of that. Then we saw memories. Memories can again be read-only memory or read-write memory, which are RAM. I can read to the memory or I can write. I can read from the memory or I can write to the memory. All that is part of sequential circuits. And any using these combinational circuits and using these sequential circuits, I can build bigger designs out of it or bigger design blocks out of it. So what I mean by that is, let's say you take inside a processor, any processor, one of the key blocks is the ALU, arithmetic and logic unit. Arithmetic and logic unit can execute any arithmetic instruction or logical instruction on that processor. So what are the arithmetic instructions? You can add certain numbers, you can subtract certain numbers, you can multiply numbers, you can divide numbers. Those are the typical arithmetic operations. What are the logical operations? I can logically OR certain numbers. I can logically AND certain numbers. Logically XOR certain numbers. Or I can shift the numbers. So it can implement a shift register. So all these basic circuits, basic combinational circuits and sequential circuits, I can use and combine them in certain fashion to build bigger designs or bigger design blocks out of it, like a ALU. So apart from ALU, then I can design some other block, like a timing control unit and other things, which will then again, if I combine all of these blocks together, I build a processor out of it. Processor is a bigger block compared to other blocks. But the starting point was combinational circuits, sequential circuits. And FSMs are basically state machines which will use this combination and sequential circuit in a certain method, in a very structured and ordered way to execute them. So the thing is, I can use combinational circuits and sequential circuits to build any bigger block or any bigger logic out of it. So we will see Verilog language. How do I use Verilog to design combinational circuits? Various examples. How do I use Verilog to design sequential circuits? Various examples of them. And then how do I use Verilog to design a state machine, which is again two kinds, mealy and mood. How do I design? How do I use Verilog to design a Moore FSM or a mealy FSM, which will then internally use combination and sequential circuits? Once you see this and once you know this, how to do this using Verilog, then you can use Verilog to build bigger blocks. So the focus will be how do I use Verilog in two different modeling formats, structural modeling and RTL modeling or behavioral modeling as we call it. Using these formats, how do I design combinational circuits? How do I design sequential circuits? How do I design FSM finite state machines? That is a section that we'll see later. Okay.
Okay.
Any questions?
Sure. Nothing as of now.
Okay.
No.
Okay, so we'll stop here today. So the next class we'll start looking at the language itself. Okay, the syntax of the language itself. Examples.
Do
So
we have to install any software before the next class?
not at this time, but later on you can. There is a simulator. There is actually an integrated software by Xilinx. So if you go to xilinx.com, Xilinx, xilinx.com, create a free account there, and you can download ISE software. The latest version is 14.7.
Mm-hmm.
Xilinx ISE, I for India, S for small, E for English. ISE 14.7 is the latest version. You can download that. We will use there is a simulator which is part of that software. We will be using the simulator later on when we do the Verilog. That will still take time, but in the meantime, you can get it done on your laptops.
Mm-hmm.
And there you need a license for that. It's a free license, but you will get that license when you register with Xilinx, and they will email you that license file.
Okay.
And you just have to copy that license in one of the folders and activate the license in that software. All of that is free, of course.
Okay.
But we'll need that maybe another at least a few lectures down the road. But if, in the meantime, if you have some free time, you can install it and keep it.
Okay.
If you have any problems during the installations, you will see it later on how to solve them.
Sure.
Okay.
Okay, so the next class today is Monday. The next class will be Wednesday, same time.
Okay.